Hello everyone, in this video we're going to be looking at a quick and easy exponential equation. We've done a lot of exponential equations and some are complicated, some are non-standard as you've seen I think about an hour and a half ago, the premiere. But this one is fairly simple, but for those of you who are new to exponential equations, this would be a good exercise. I'm hoping that it'll be helpful. Please let me know in the comment section down below. Now we have 2 to the power x plus 2 to the power x equals 4 to the power x. Now this could be called a freshman's dream or maybe high schooler's dream, I don't know. Because when you add the two exponentials, you just add the bases, right? But that's not always the case. For example, if you add 3 to the x and 3 to the x, do you always get 6 to the x? Or is this true all the time? The answer is no, not in general. We're going to be looking for an x value that satisfies this particular situation. So for which x values is this true? That's going to be the question, okay? And how do you add exponentials? Good question. Like whenever you have something like a to the b and a to the c, if b and c are different, can you add them? Or if you have 2 to the power 3 and 2 to the 5, can you add them? Yes, you can find the numerical values, but when the bases or the exponents are different, it's kind of difficult to add. But when they're both equal, it's kind of like having the same thing twice. Make sense? Okay, there's a couple ways to approach this problem. One way to do it is fairly simple. If you add a plus a, you get 2a. Awesome. What is a in this case? 2 to the power x. So if you add 2 to the x and 2 to the x, you get 2 times 2 to the x, because 2a means 2 times a, right? What's that supposed to mean though? How can I solve this problem? And again, you can solve this problem in so many ways. I guess we can talk about multiple solutions. You can just go ahead and divide both sides by 2 to the x, and that's going to give you 2 equals 2 to the x, because when you divide these, you just divide the bases. And then from here you can conclude, hey, x is equal to 1, right? But that's not the only way to do it. You could also do the following. When you multiply two exponents, you add when you multiply two powers, you add the exponents. So from here, this is supposed to equal 2 to the power 1 plus x. And 4 can be written as 2 to the power 2 to the power x, which is 2 to the power 2x. And then from here, you can say that, hey, 1 plus x is 2x, which again gives us the same solution. So no matter how you do it, you're going to get the same answer. Obviously, we could also look at it from a different angle. I guess the purpose here is not just give you a super easy problem that you can do mentally, but more like going over the properties of exponents in a single problem, because notice that we're using a lot of different properties. Hopefully this will be good practice. Okay. Now another way to look at it is, since 2 to the power x is a common factor, we can take it out. What do you get inside? 1 plus 1. That's what's really cool about factoring. Don't you love that? It becomes 2, and now again we can divide both sides, and 2 is going to equal 2 to the x, and you can proceed as before to get x equals 1. Make sense? Okay, great. So that pretty much sums up the solution. I don't think there's any other way. Maybe there is. Who knows, right? I mean, there might be another way to do it. Obviously, you could do the following as well. I just thought about it. You can call this a, and then that will give you a plus a equals a squared. And then this gives you a squared equals 2a. And then you can kind of bring these on the same side. And then factor out an a minus 2. And from here you get two solutions. Great. A equals 0, a equals 2. Wait a minute. Isn't there only one solution? Yes, because the problem is if 2 to the power x is equal to a, notice that 2 to the power x can never be 0. Even with the complex values, that's not going to happen. Therefore, a equals 2 is the only value, and from here we get x equals 1. But what makes this problem, I think, more interesting is the complex solutions. Let's go ahead and explore if you can find any complex solutions from here. So here's how it goes. You can go ahead and add these up together just like before, and that's going to give us 2 times 2 to the x, 4 to the x, and then 2 to the x equals 2, and x equals 1. But that's the real solution. Let's go ahead and complexify the right-hand side. We can go ahead and write the 1, which is invisible in this case, right? You see the 1 now? We made it visible. That was in invisible ink. Now we're going to replace 1 with e to the power 2 pi n I. Because if you think about the Euler's formula and the polar form of the complex number, remember it was e to the power I theta, which could also be written as cosine theta plus I sine theta. You notice that theta represents the angle that the number makes with the real axis. So if you have a complex number graphed or plotted like this is theta, this is the r. By the way, r is the modulus, so if our number is z, then you can also set this equal to the absolute value of z. What are we talking about now, though? We're talking about 1. So 1 is actually going to be a real number with no imaginary part. This is the real axis, this is the imaginary axis, remember? So our number is actually going to be on the real axis, on the positive real axis, 1 unit away from 0. So its angle is going to be 0 degrees or 0 radians or whatever, or 2 pi or 4 pi or multiples of 2 pi. That's where I get this 2 pi ni from. Make sense? Great. So here's what we're going to do. There's a couple ways again to proceed with the solution, but if you go ahead and just follow one of them, I think that's going to be good enough. I don't know. We might talk about both. So one way to do this is divide both sides by 2. That's going to give you x minus 1. Solve for x minus 1, and then you'll get x by adding 1 to both sides. I talk too much. Let's get to work. Now, I'd like to natural log both sides, but wait a minute. I don't have an e on the left. I want to change the base. To change the base, are we going to use change of base formula? Well, kind of. We're going to use the identity 2 equals e to the power ln 2. Replace the 2 with that. You're going to get e to the power ln 2 multiplied by x minus 1 equals e to the power 2 pi ni. Wait a minute. We don't even need to ln both sides because it's kind of obvious, isn't it? The exponents are equal. Great. So now let's go ahead and set them equal to each other. X minus 1, I want to write that first, times ln 2 equals 2 pi ni. And then the next thing you can do is, there's again so many ways to go about this problem. You can go ahead and distribute and then isolate the x, or just divide by ln 2, which is what I'm going to do, and then add 1 to both sides, which is fine, right? And this is really cool because when you add 1 to both sides, this is going to show you the components, which is really nice here. Let me talk about what I mean here. Notice that n is an integer. Wow, did I say that? I'm sorry if I forgot. Apologize. N is an integer, and you can replace n with any integer value, including n equals 0. What happens if n is equal to 0? You get x equals 1. Wait a minute. Didn't we find that before? Of course. That's the only real solution to this equation because we complexified it. We totally forget about it, right? And now, notice that this is a general solution. So if n is equal to not 0, then of course you're going to get all the imaginary, or I should say complex solutions. But there's a real part, which is 1, and there's an imaginary part, which is 2 pi n over ln 2. N is an integer, and you get infinitely many complex solutions. And this brings us to the end of the video. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.